Hi everyone, Mr. Neighbor here, and we're going to start talking about Chapter 13, which is Work, Power, and Machines. So first, work, energy, and power. So work, energy, and power are words that have certain meanings in the everyday language, but when we come to science and physics, they have a different meaning entirely. So you might think you're doing work in the normal sense of the word, but in physics, you're not actually doing work. So we have to be careful about how we talk about these. So first, work. Work is defined as a force applied over a displacement, sometimes thought of as a distance. So if something does not move the object, it is not applying any work to the object. So note that the force and the displacement, or the distance that the object is moving, have to be in the same direction. So that's the only way work is being done. Work is labeled with a J for the units, and that stands for joules. That's the same label that we'll use for energy as well. So the formula that you would see a lot of times is the force parallel times the displacement, or the distance. So you might see a D written right there, but it's force times the distance traveled. So let's do a few practice problems here. All right, number one, a scientist giving a speech to a class. So is there a force being applied over a distance? Nope, so there is no work being done. A teenager mowing the lawn. Well, if you're mowing the lawn, you're pushing the lawnmower. That is if you don't have a rider. But in most cases, you're pushing the lawnmower in the direction that the lawnmower is going, so you are doing work. The force is in the direction of the displacement, so yes. All right. A professional bodybuilder lifting weights. So the bodybuilder would be lifting the weights upward, and that means there's a force upward and they're moving upward, so there is work being done by the bodybuilder. There would be negative work being done by the force of gravity, though, because gravity's force would be pushing down while the weights are actually traveling up. So that means there's negative work being done by gravity, but there's positive work being done by the bodybuilder because his force and the displacement are in the same direction. Gravity is going opposite the displacement. A person moving furniture up a flight of stairs. That would be a yes. There's a force pushing the person upward, and those boxes are traveling upward. Or you can think about there's a force pushing the person with the boxes forward as they go up the stairs. So, and the boxes are moving forward. So yes, there's work being done in that direction as well. A person pushing against a locked door. So assuming the door doesn't move at all, that would be no work done because there's no displacement. All right. 100 Newton horizontal force is used to drag a 20 kilogram box 2.0 meters across a frictionless table. How much work is done on the box by the horizontal force? So this force is being applied right here. So we have to multiply that force by the distance it travels. So work is equal to the force parallel, which would be the 100 newtons, multiplied by the distance that it travels, 2.0 meters. When we calculate that out, we will get 200, and with significant figures, there only needs to be one. So 200 J capitalized for joules. How much work is done by the table? Well, the table would be the normal force part of this. And the table isn't moving the box at all in the direction. So the work done by the table, because it's not applying any force parallel to the displacement, there is no work being done. So 0 joules. How much work is being done by gravity? Well, gravity is also not moving the box at all in the direction that the force is going. So because it's not moving it in the direction parallel to it, it also is 0 joules, no work being done. Here we have the same 100 Newton horizontal force that is being used to drag the 20 kilogram box 2.0 meters across a rough surface at a constant velocity. But now we have friction. So how much work is done by friction? So remember, work is the force parallel times the distance or the displacement. So it could be delta x or d if you want to think about distance traveled or displacement. Most often people think of this, but truly it's the displacement. So the force being applied, well, our force is opposite the displacement. So that's going to be negative 100 because those arrows, it looks like, are the same magnitude. I'm talking about the force applied arrow and the friction arrow. So assuming it's moving already, this is a net balanced system. All the forces cancel each other out, but it's still moving, but it would be moving at a constant velocity. And we times that by the displacement, which is still 2 meters. So here we will get out negative 200. So the negative tells us the force being applied is opposite the motion. So we do negative work. All right, now we have a bowling ball that we're going to talk about. So if I lift an 8-kilogram bowling ball up 50 centimeters into the air at a constant velocity, how much work did I do? So if we want to do a free body diagram of this, if it's at a constant velocity already, that means my force applied is going to equal my force due to gravity. So it is in equilibrium, but it's dynamic equilibrium. So to find work, I have to take my force parallel to the motion, which is the weight force equal to the gravitational force. So that would be 8 times 10, roughly, to give me out my weight force. So force due to gravity is equal to that, 80 newtons. So that means the force that I'm applying is also 80 newtons and 50 centimeters. Remember, I have to convert that into meters, which would be 0.5. And when I multiply that out, I will get 40. And with sig figs, that should be right. And that would be joules. So how much work did gravity do? Well, gravity is the same force, but in the opposite direction. So the only thing that's going to be different is we're going to put a negative for this force. So it's 80 newtons. The displacement's the same, 0.5. And then we will get out a negative answer of negative 40 joules, signifying the force was done in the opposite direction of the displacement. How much work do I do lowering an 8-kilogram bowling ball 50 centimeters down? So this is a different problem. So let's look at a different free body diagram. So now the force of gravity has not changed whatsoever. It's the same magnitude. But since I'm lowering it, that means I'm applying less force myself. So the applied force is less. So the work that I do is this force applied vector. So work is equal to my force. My force would still be 80. In this case, we're not given too much information right here. So because the force wasn't really defined for us, we have to kind of assume it's 80. We don't know enough otherwise. So this arrow should be the same length as the force due to gravity, but now the dynamic equilibrium is a constant motion, not upward, but downward. So it's negative 80 now because I am applying an 80 Newton force upward, but I'm still lowering my hand downward. So that's opposite the displacement, which is 0.5 meters. So now my work is negative 40 joules because the displacement has now changed. How much work are you doing when you hold the ball motionless? Well, when you're holding it motionless, there is no displacement. So that means when you multiply by 0, you're going to get out 0. So no work being done. Even though it seems like it's heavy, you're not doing any work. And lastly, really quick, if you're carrying a ball sideways, your force is up, gravity's force is down, but your movement is not in those directions. So technically, no work is being done there either. But there is a little bit debate that could happen with that problem.